to our last talk of the morning sessions. Okay. Our last talk of the morning session is by Shiji Lyu from the University of Illinois, Chicago, and he'll tell us about approximation and complete local rings.
Okay, thanks for the introduction. And before I start, I want to say one of the works of Professor Karen Smith that I'm pretty fond of is the characterization of rational singularities as the local cohomology does not have invariant submodules. Even though I'm not going to be talking about singularities at all, I think in this talk. Yeah, I did work a little bit on that, and I really like that result. I don't know if anyone mentioned it yesterday because I just learned today. All right, so good news is I did make it here, and let's get started on this approximation of complete local rings. So this is a pretty vague title, and I did that because indeed our constructions work with very little restrictions, but the most applications we'll find will be in the case of equal characteristics 0. Because the equal characteristics 0, many results have this restriction that your ring has to be finite type over a field, right? And that's because we also apply geometric methods, for example, analytic methods using complex geometry, right? And also reduction modulo P as used in first talk of the day by Hagi somewhere. Yeah, okay. Okay. Harder to find what is the most obvious spot. So you read those theorems, and let's not the let's give some explicit situations to think about here. So let's say A is a local ring that is essentially finitely generated for finite type over a field of characteristic 0. And let's say it's normal. So what you would do to detect the singularities of A, just generally speaking, you take a resolution of singularities of spec A. So X be spec A, and Y be a resolution of singularities. And you can say a lot of things about the singularity of A using one or an arbitrary resolution of singularities. So, for example, A has rational singularities. So I name this half by F. So the higher push forward of the structure shape of Y are 0. So doesn't matter which resolution you choose. You can use the resolution singularities and cohomology of coherent sheaves to define singularities of the original ring A, or any algebra variety you prefer. But there are other results that are not definitions, but definitive results. Along these lines, for example, there's a theorem, generally referred as Grau-Friedman-Schneider vanishing. And it says that you always have Ri at lower star of omega y be 0, or 0. And here omega y is the canonical bundle of y, has to be compatible with x in some way to make sure this holds, but I will not get into details of that. So this theorem is one of the bases, that this definition is good. And with rational singularities, there are many theorems regarding rational singularities without connecting it to other types of singularities such as KLT. And there are also results about deformation of singularities. So this is a theorem that I'll pick. That says let A be non-zero divisor if the quotient has rational singularities, then so does A. So of course, it's not that easy to relate to resolution of singularities of these two things. So it's not trivial, it's not easy. And geometrically speaking, it says if a Cartier divisor has rational singularities, then the original variety has rational singularities around that Cartier divisor. And all of these are for local rings, essentially finite type of field characteristic 0. Of course, they work for global affine coordinate rings as well. For local rings, you need this restriction. For affine rings, you need the whole ring to be finitely generated over a field. And that's originally because, for example, for Grauer, Riemann, Schneider, right? The common proof goes through Bogdan's vanishing theorem, which was proved using complex analytic methods, and then later proved using reduction modulo P algebraically. And none of these are available if I remove this essentially finitely generated over a field condition. So what if we look of residual characteristic 0? Of course, if it's not of residual characteristic 0, we cannot expect so as good as this. I'm just trying to not change the essential sort of characteristic picture, but removing this finite type over field restriction. And this is very important, even if you only care about varieties, because you do need the complete local rings and schemes over them to sort of find the standard forms of singularities, to simplify, to do induction. And in fact, originally, the resolution of singularities was proved for all finite type schemes over complete local rings with residual characteristic 0. So that induction actually works better. And there are also other situations. For example, we consider the chain condition of log canonical specials, or some others like uniform type result that concerns ascending chain condition or uniform boundedness. You won't have some result over complete local rings. And not to mention that they're just natural objects by themselves. So now, given that the original method was not available, now can you do something? And the answer is generally yes. You can try to read the original proof and see if you can apply the method, or you can try to approximate your complete local ring using these local rings essentially finite in general. So, for example, the Grauer Riemann Schneider vanishing and other tonal type vanishing theorems was proved by Layama. So GR works for complete local rings. And his proof is by a very specific approximation method. So he proved these vanishing theorems both for over complete local rings, for resolution singularities and more, formally using the original result for algebra varieties. But this approximation method does not work for Alking's theorem. So if you use the same approximation that he did, it won't work for this, and it won't work for other situations. So,
Shiji, there's a quick question. When you say, I thought Elkick's theorem just needed Grauer Schneider.
yes, but okay. So that will be true. So if you read the proof, if you read through the proof and apply the method, it will work.
Yes.
But if you just do the same approximation method, try to deduce it formally from this result, then it doesn't work. So if you forget about this, but only approximate the rings and apply this result formally, it doesn't work. So our goal is to develop a systematic approximation sort of scheme or method for complete local rings that will deduce your results formally from the case of algebra varieties. So that is the goal. Yeah. All right. So and it turns out that there are many things that we can do, and our result will give you many corollaries. So, for example, our approximation method will recover Zavyalov result. It will generalize L-K's result to the complete local case. And also, let list one more thing that the original proof definitely does not work, which is generalize certain multiplier ideal formulas to this case, to the complete local case. So those include multiplier ideal formulas by Takagi. So for example, Takagi had this subadditivity. So I'll just write this down without giving any definition because it will consume too much time. Something like this. Smash. So it's T plus U. I think this is correct, so assuming it's equal. Now the original proof uses reduction modulo P to the characteristic P, and then use test ideals. So that's only available when you have a field to work with. In a complete local case, you cannot reduce modulo P.
So right hand side is.
Oh, no, this one, right?
Yeah.
I always confuse these two. Yeah. Okay. Thanks. Sorry about that, but the point is, our method is very robust and very systematic in the sense that, in many cases, scenario we don't need to know what the original proof is, whether or not it can be generalized. We can deduce the result formally, and that will save us a lot of effort. Because, for example, to understand L-K's proof, you might need to read French. So I'm not perfectly sure if it works. Yeah, and you could also generalize the corresponding result by Kovac and Shri on Dubois singularities. Now, let me tell you what is so I have told you what the approximation argument can do. It can give you recover, or generalize the results known for algebra varieties to complete local rings, and also by extension to all quasi-excellent local rings. or quasi-excellent schemes by taking the completion. So now let me tell you what is the approximation argument itself. Before I do that, any questions regarding that thought so far?
Talk about like Pascal's neuron desingularization. That's what you mean by approximation?
Yeah, it is. Essentially, it is. Yeah, that's the key ingredient in this argument. So you apply Pascal's general neuron desingularization to write the complete local ring as a filtered co-limit of these rings, and then what it must do is to show that this is robust enough that it preserves properties such as normal or regular or rational singularities or not. So that can be a natural starting point. So what is the approximation setup? So given a complete local ring, I can always apply Cohen-Structure theorem. So A will be finite over our series R will be finite, where R is the ring of this form. Our series ring where K is a field of characteristic 0. And R is the completion of R0, which is the corresponding localized polynomial ring. So R is the completion of R0. So we know by Pascal's theorem, general neuron desingularization, I know R is the filtered co-limit of rings Ri, where each Ri is smooth local over R0. So they are localizations of smooth R0 algebras. In particular, they are essentially a finite type over the field K, and also they are regular local rings.
So just to clarify, this is all in characteristic 0.
Yes, but the same thing will work in characteristic P or mixed characteristic. It's just in that case, we don't get that many corollaries because in those cases, the proof already works for complete local rings, for example. That's why. And this definitely works in more general situations, even non-local rings as well. But then you need to take caution because some of the constructions might have problems. So by standard theory approximation that appeared in the EGA, for example, you can always find, so R is the co-limit of those Ri. So you can always find a finite R phi algebra AI whose phase change is A. So this is the other direction. So, and this will be a Cartesian diagram. And you can do that for your resolution of singularities as well. This will exist, and this is a diagram. So you can always sort of descend your data, your spec K, and your resolution of singularities down to the level of the individual RIs. Question?
Do you have an example of an A of this form which is finite over this kind of paper, which is not completion of a finite type algebra at some prime ideal?
Oh, that's a good point. So if you ask me, do I have an explicit example? The answer is no. I think they do exist, but I've never looked at any explicit example, but I think they do exist.
Okay, so what I mean is that if A is actually completion of a finite type algebra over a field at some maximum, then probably will use the Pascal's theorem for the regular map itself.
Well, in that case, you could skip. So in that case, you could skip this R.
Yeah, exactly.
You could totally skip this R. But I have no idea if you could, for example, that A, if this little a is not in your, if A is a completion of some AI, but your little a is not in that original smaller range, then you cannot apply L-Higgs result. You still need to be potentially apply a construction like this. All right, so the point is we could always approximate these morphisms, and I can make sure that, for example, this is proper and this is finite. But the problem, there's at least two problems that you need to overcome. The first is AI still normal? And Y still regular? Right, that's the first problem. And generally speaking, you cannot expect this if this system of rings is arbitrary. So you could always descend like properties, finite those relative properties of morphisms.
Shiji, there's a comment in the chat.
Uh-huh.
It says Whitney gave an example of a singularity. This is from Janusz Kolar. It says Whitney gave an example of a singularity that is not completion of an algebraic singularity.
Answering
So
Alex's question.
that's the same question. So yeah. So the first problem is whether or not the absolute properties of the scheme is preserved, and this is not answered by Gorsinik. I think it's generally not true if the system were arbitrary. And the second problem is how do you compare these cohomology modules, right? What's the relation between Ri at lower star y and the corresponding constructions on this level? So I'll just write cohomology and phase change. And in Mulayama's construction, this is process using a clever method by passing to all resolution singularities, do not compare the individual ones. And that exactly works in this situation, but not in this situation, and not in this situation. Right? But our method directly solve all these problems so that you could work with one fixed resolution. And when you go downstairs, you will always have these properties preserved, and you can sort of directly calculate the multiplier ideal formulas just by base change, as well as sort of dimension theorems by base change. And because you can also calculate these modules by base change, you recover Alex's result. Now, let's see how much time do I have. Well, let's start.
Give him about 5 minutes.
Okay, that's great. So that's exactly enough. And the solution for the dilemma is that for large, this is I, X, I, and so here Xi is expect AI, so I'll just write AI, and R for independent over Ri. The same for any Y, or any other scheme you want to approximate. So core independence basically directly give you cohomology and phase change, and it also gives you that normality and regularity are preserved. So if you're not familiar with core independence, let me just give you an intuitive explanation in this particular case. And you can see why the first problem is solved. Maybe it's not a good way to see why the second problem is solved, but that one is rather formal. So what we're doing here is I have this R0 going to Ri, going to R. So if I take the completion of these rings, this is unchanged and it equals this, right? That's what our construction begins with. So in substance, Ri is the power series string that has more variables, and this is a surjective map of regular local rings. And being a surjective map of regular local rings, the kernel is generated by part of the regular system parameters. In particular, it's generated by regular sequence. So you could say that spec R is a complete intersection in spec of Ri hats. And this Tor independence condition, Tor independence, exactly says that the same regular sequence stays a regular sequence on the level of A and Y. So let's say this regular sequence is rho. Rho is a regular sequence. So I do need to take this phase change to completion. And it tells you that Y is a complete intersection inside this phase change. So if your Y is regular, it's a complete intersection in this guy. This guy is also regular, and then you can remove the hat by a flat descent. So now you know Yi is also regular. That's why our approximation preserves normal and regular, at least for proper schemes. For non-proper, you need more arguments. And by the same reason, it also preserves properties such as reduce or SK or Gorenstein or Cohen-Macaulay. And because it preserves regular, because it preserves cohomology and phase change, it also preserves rational Dubois singularities. So in fact, you can say a finite type scheme over spec R has rational singularities if and only if all of its sort of descent schemes over spec Ri has rational singularities. And therefore, you can formally get LP's theorem without knowing anything about this proof. And it works with other type of singularities as well. So I think I do have 2 minutes, right? So let me do mention something that you cannot do with this construction, is that you cannot do sort of existence type results. Let's say you can run MMP over each spec AI. Do I now know I can run MMP over A? The answer is no, because the base changes may not be compatible. So you cannot say, okay. Well, on the other hand, we know we can run MMP over spec A. This is joint work with Mulayama, starting from here, just by repeating the method of transition to 0. That's very different from this. This is formally deducing results. And I work with Mulayama to sort of repeat methods to do the MMP. So if we combine these together, we can run MMP for finite schemes over spec R. And then looking at the results of MMP, we can say they may satisfy some properties that are expected using this formal deduction method. So you can combine the 2 ways of formally deducing and repeating the method, and it will give you more corollaries. Now, of course, there's no complete list, and I don't know what you want, but there will always be a chance that it's possible. So yeah, that's all I want to say. Any questions?
Does your key lemma work in non-equal characteristic 0?
Yeah, it works in arbitrary characteristic, and it works for any works more generally. So, for example, you only need to have any system of local rings such that this is a local complete intersection map. Always. Now, you do need to be a little bit careful if your Ri is not excellent. Yeah.
Sorry, just clarifying the key lemma maybe. So you're saying for any approximation Ri for large I, this will go independent.
That's correct. So it doesn't matter what Ri or the AI you choose. So these Ris are highly non-canonical, and there's no way to.
Okay.
Well, if you give me 2 systems of Ri, there are some maps between them. But it doesn't, yeah, it's not fun. Of course, once you fix those Ri, then it's are the same after passing to such large indices.
More questions? If not, let's thank Shiji again.